We're gonna go to our next presentation from University of Washington. Dr. Don Lehman will present on impact of construction eccentricity on direct pier-to-pile connection for permanently cased shafts, shaft piles. Dr. Lehman?
So this, for those of you who maybe have been attending these for a couple of years, you know that Charles Roeder and I have been looking at concrete-filled tubes, either as a superstructure or we've been really focusing on it as a substructure, which most of us term a case shaft. And so we've been looking at different types of connections, and this is really two projects sort of put together. We originally were going to look at reinforcement eccentricity explicitly, but unfortunately, with our setup in the lab, it became very difficult for us to look at that eccentricity. So instead, we're going to do it a little bit differently, which is to look at the impact of enhancing the bond within this connection and how it impacts the response, including the progression of damage. So it might be a little repetitive to what you've seen before, but I think to put it all together, this makes the most sense. Given the fact that I don't have a lot of time, I'm only going to talk about the experimental work that we've done and what it implies in terms of design. So here, what we really are trying to do is look at a reinforced concrete pier directly connected to a concrete steel tube pile connection, case shaft, however you like to term it. And we looked at a couple of different things. So the first thing we looked at is what is the impact of the pile diameter? And it's really the pile diameter relative to the pier or column diameter. I have to say we've gone to columns because there ended up too many P's in our subscripts. But so pier, column, we'll kind of use those interchangeably. The second thing is, is the AASHTO embedment depth adequate for this connection? And then the third is what happens if we try to enhance the bond? And this is really what I want to focus in on, because there's a temptation in composite to think we've got to have these additional bond mechanisms everywhere. And what that actually can do is impact the concrete in a negative way. So we're just looking at one place where we enhance the bond. We've been doing this in other projects too, but it's something I want us to think about in terms of how we design composite systems. So this is just our general specimen design. It's about 1/2 scale, more or less. The column diameter is 20 inches, and the pile diameter is either 30 inches or 48 inches, like I had just shown. In all cases, we embedded the reinforcement to the AASHTO embedment depth, and we were using number 7 bars in terms of the column longitudinal reinforcement. This bottom connection that you see here is something you might have seen from us before, because this is our connection of a concrete filled tube into a block, like could be a beam, a cap beam, could be foundation. Here, it's just to transfer the forces into the block, and this is kind of where the eccentricity was giving us problems, because clearly we can't make the column itself eccentric with the way that we're loading these specimens. This is just a photograph of the specimen to give you some idea. You can see that we're embedding the reinforcement and continuing the hoops. Now, whether or not you really need to continue the hoops all the way down is a discussion we can have, but this was sort of the preferred way based on what the advisory panel had given us as feedback. So you can see we've got a steel can at the very top, and this is really just to provide the confinement for the loading. It's not really part of the specimen design. So I'm going to present 3 specimens. We actually have 4 specimens, where the 4th specimen was something we did in conjunction with peers. So this is a collaborative project between this ADC center and the Pier Research Center. And in general, we looked at, like I said, 2 different pile diameters, which you can see they're 30 or 48 inches. And this last one, they all have the same embedment depth, which is 21 inches. And the last one has an R, which is the ring. So we took these specimens and we added a ring right below the top of the steel tube. So 2 inches below. So twice the cover, essentially, is what we're saying for that depth. And that's based on a lot of analysis that we've done and that we've talked about previously. And you can see these are just the materials for what we are testing here. pretty standard materials. So I'm just going to give you a little video to look at. These are just images put on top of one another. You can see that we're cycling the column back and forth, and then you can start to see some spalling. As we continue to cycle, you get a lot of bar buckling. Eventually, we get quite a bit of damage here. This is actually the specimen with the ring, which is for this 30-inch pile to a 20-inch column, gives us actually the best results. In general, what I'm going to talk about are the different damage states. So for most of you, you know these states: initial yielding of the longitudinal reinforcement, then spalling and buckling of the bars. In some cases, we had bar fracture, and eventually we get failure, where you can see we get a lot of horizontal movement. Now, hopefully you'd never get to this point in an earthquake, but we can get to that point in the lab, which we always want to do, right? We want to complete the full failure mode. So this is just the general behavior of this specimen, and what you can see is that we have initial yielding here at about 1% drift, and then spalling at about 5% drift. And you know, this spalling at 5% drift is pretty good, because if you look at the response of most bridges, you really aren't going to have demands much beyond that. And this is a repairable damage state. So we're happy about this behavior. And then we get bar buckling and eventually failure at 8% drift, which obviously is very, very ductile response. If we then go to the 48-inch, of course, we have slightly different responses here. We're getting yielding a little bit less than 1% drift at 0.75% drift, and then again spalling at a little lower drift, and then the bar buckling doesn't actually happen until almost 9% drift, and we get failure at almost 10% drift. And then finally, this specimen is just like the first specimen that I showed you, but in addition to embedding the reinforcement 21 inches to meet the development length, we added this ring. So just one ring located 2 inches below the top of the specimen. And what you see here is we yielding at about somewhere around 0.5% drift, spalling at a little bit higher, 5.5% drift, and then again, this specimen gives us bar buckling at almost 9% drift and failure at almost 10% drift. So, you know, although it may seem subtle, we are getting a benefit of this ring. So I wanted to show you these envelopes. These are just first cycle envelopes. The blue is our standard reference specimen, and then the orange is that same specimen, but it has a larger diameter, and you can see in both the blue and the orange, we start to lose capacity somewhere between 6 and 7%. Whereas when we add in the ring, we actually get beyond 8% without any loss in strength. These are the damage states. As I said, the yellow one is LD is for a long duration, which I'm happy to talk about later on, but I'd rather have us focus in on these other 3 specimens. So the 30-inch diameter pile, the 48-inch diameter pile, and the 30-inch diameter pile with this supplemental ring. And what you can see is that this ring gives us this delay in some of these more severe damage states, which is important when we think about functionality of a bridge or other elevated structure that's going to be using these connections after an earthquake. And so although we can't maybe see it so much in the force displacement response, we do see it in the damage. And I wanted to show you these specimens. So this is the 48-inch specimen. You can see where the column was. You can see all the reinforcing bars. We were about 2% in terms of the longitudinal reinforcement in the column. So a pretty standard bridge column. And you can see the cracking in the concrete. I call this the bonded concrete. So the concrete between the edge of the reinforcing bar to the interior of the steel tube. And you do see some, a little bit of damage around those bars, because although it's subtle, I think if you look back to column foundation connections, other connections, you will see that it's pretty common to have pretty severe bond damage. Kind of goes to what Professor Thonstadt was talking about. These 2 specimens are on the left, the specimen without the ring, on the right, the specimen with the ring, And what you can see if you look at the specimen without the ring on the left, you can see there's more damage to the concrete around the bar than the specimen on the right. It's a little subtle and it's very difficult because these are down in the connections. But this additional ring is allowing for the bond demands to be reduced down into the pile, which kind of saves those that part of the response. The last thing I want to present, because I know I don't have a lot of time, but I think this is really important, is to look at the displacement contributions for each of our specimens. So what we're seeing here is there's a blue deflection, which is attributed just to flexure of the pile. And if you think of the pile flexing, at the top of the pile, there's a fixed end rotation, and that's what the orange is. And then if you think about the connection is really the region where the bar is embedded into the pile. And then the last one is column flexure, which I think we all know about. And so, of course, not everything reached 100% because there are errors, unfortunately, in these measurements. But I think what you see is if you go from 1% drift, which is about twice yield, right, somewhere around there, and we increase that displacement to about 2.5%, what we're seeing is the connection really starts to contribute. And if we go to 4%, and then 5%, again, you see that that gray bar is pretty high in terms of the overall contribution. Now, this may seem counterintuitive, but what's happening is, you know, the flexural response of the column, the ductility is really through yielding of the reinforcement. And if you take that bar and you have a portion of the embedded bar having a fairly large strain, and then that strain lowers because of the bond between the reinforcing bar and the steel tube, you actually get a lot of inelastic action out of that region. And so in all cases, really, with reinforced concrete connections into another component, be it a pile cap, be it a spread footing, and in those cases, we also see large connection contributions. Not as large as this, but this is a very kind of unique test, and it is something that is important for us to remember. So just taking those specimens as a whole, what we see is that the specimen without the ring shows lateral strength degradation. That's also true for the long duration specimen. And these, when we look at the amount of concrete to the bar diameter, we were somewhere about 8 times the bar diameter. In contrast, we saw that specimen 4821 and really 3021R didn't show as much lateral strength degradation in terms of cycle within a cycle. And one of the things we know from that, adding that rib is allowing the specimen to act as though it has a lot more concrete. And that really gives us something to think about when we think about eccentricity in terms of reinforcing bar cage placement, that with that eccentricity, even if you move that cage closer to the steel tube, having that ring will give you that enhanced bond. And so eccentricity becomes a lot less of a problem. The damage states that we saw, very, very similar for other reinforced concrete column tests, going from yielding, spalling to failure. The displacement contributions primarily, as we said, are due to the connection and the column flexure. We're not getting a lot of displacement from the pile, and we don't really want displacement from the pile. We want the pile to remain as elastic as possible, so we don't need to compare it. The other thing I think is that pile size is important. So if you don't add an embedded ring, you're going to get a better behavior and less damage if you have a larger diameter pile. So again, you know, we had a column diameter of 20 inches and a pile diameter of 48 inches. So that's more than twice the diameter of the pile. But I do also think, although we haven't studied this experimentally, it's also important to think about what that concrete area or thickness is or dimension is relative to the bar diameter as well, since we know that the bar, you know, a larger bar is going to need more concrete to allow the struts to develop from those deformations. What is the effect of embedding the ring in the pile? Well, this embedded ring, it reduces the impact of column eccentricity because of the enhanced bond and the fact that we're actually bringing those struts down further into the connection. We're seeing a reduction in slip of the concrete, which of course makes sense, and it delays reinforcing bar buckling. So our recommendation is to add a single rib at a distance of 2 times the cover below the top of the steel tube, below the top of the pile. I also want to say, as I said in the beginning of the talk, additional rings were not beneficial. And if you think about the concrete and the strutting action within the concrete, if you have multiple rings, you're going to have more and more demand on those ribs, and you're going to actually maybe even increase the damage into the pile, which is incredibly hard to repair. So this ring also gives us that advantage. It really reduces the impact of eccentricity, and it reduces the damage, the bond damage and degradation. So that was, I think, pretty short and quick. This funding has been provided, obviously, by the FIU ABC Center and Pier. This is a photograph of all the students who are helping with the tests. Yes, testing in the time of COVID. So there's obviously everybody was masked up and very safe, and you can see a specimen behind them. And with that, I'd be happy if there's any time to answer any questions. I know that we're sort of short on time. If you're in Seattle at this time of year, please come visit the cherry blossoms. They're really, really wonderful. So with that, I'd like to thank you and turn it over to whoever needs to go next if there isn't time for questions.
Thank you very much, Dr. Lehman. Yes, I know about cherry blossom as my daughter. My daughter has admission from UW, and I think cherry blossom is acting like a determining factor in
Well, I have to say, during COVID, they didn't want anybody visiting, so now people are really excited that they can go back. That's really beautiful. It's a wonderful time on campus.
Yes, I've heard so. Thank you very much. Again, in 20, 30 seconds, Dr. Lehman,
yes.
When is that? You mentioned you almost closed with that ring thing for improvement of behavior. When is that the engineer designer should consider that? When would you recommend?
So my recommendation would be to look at, so we haven't been able to do this, but I think my recommendation would be that unless your column, your pier to column diameter is 2 or more, I think the ring is going to give you better response. And also for DOTs that are concerned about post-lateral demand damage. So that doesn't just have to be earthquakes, right? This could be hurricanes, tsunamis, lateral spreading, lahar loading, other things. So in any of those cases where the engineer, contractor, and the owner do not want to have any damage within the pile, I think the ring, which can, be prefabricated, and we put down a little bit so that, one, we're not over damaging the cover, but also in terms of those driving forces, we don't want that to be at the top. We're worried about that in terms of constructability. But right now, I have to say, with what we've seen, we are really recommending that in most cases, the engineer adds this ring. We really see it as beneficial both to ductility and also enhanced bond. And the other thing I just want to say quickly is, you can end up with, unfortunately, some pretty crappy concrete at the top of your pile, right? Because of the top casting issue, and you have more water. I think the ring also alleviates the impact of that. So our recommendation right now is really, for most of these connections, we would recommend that single ring.
Thank you very much, Dr. Lehman. Thank you again.